So, hello, everyone, and welcome to Spectral Geometry in the Clouds. Today, it is our pleasure to listen to Yannick Bonthonneau, who will talk to us about the 2D pure magnetic tunneling formula. Do not hesitate to ask questions during the talk, either by the chat or by talking. You're very welcome to do so. Yannick, the floor is yours.
Okay, well, thank you for the invitation. Before I go, I talk about the content. I need to say that this is a work that's not already on the internet, so it's not yet available. And it's joint work with Soren Fournais, Léo Morin, and Nicolas Raymond. And because Nicolas Raymond is part of the authors, it's about the magnetic Laplacian. And so we're dealing with tunneling effects, and the only other result of tunneling effects is by also Soren, Leo, and Nicolas a year ago, and this is answering a question from I think at least 96. So it's a relatively old question. It's maybe a bit surprising that took so long to find an answer. Okay, so I think maybe most of you have heard the words magnetic Laplacian, but maybe not all of you have already encountered it in person. So in the two-dimensional case, we're going to take two smooth functions of x and y and take a small parameter, positive, and put this operator. So we're going to take some squares, and inside each square, we're going to twist a derivative. So this is, it depends on a, the function's a, but what's really important is the function b, which is something that looks like dA if a was the one form ax dx plus ay dy, okay? So if we think of higher dimensions, or instead of working with R2, we're going to work on a surface, a supposedly is a one form, and then this square here is actually d star d, where d is a twisted derivative by the one form. Okay, so there is a geometric interpretation to this formula, but for today, we don't really, I'm not going to get into such considerations. And here, the important thing is that we needed an a function to define this thing, but we also needed the flat metric, which is, implicitly in the formula. Okay, so it's called magnetic Laplacian, but as far as I understand it, it's not really a good model for the dynamics of electrons inside of a purely magnetic field without electric field. Okay, so that's not really a physical motivation. I think that the true physical motivation comes from superconductivity, where if you take b to be a constant, this operator is related to the linearization of some functional regarding superconductivity something, which is completely beyond my physical knowledge. So I'm not going to talk really more about this. The key thing that takes place here is that if b is a positive constant, then the spectrum of this operator is comprised of isolated points, and each of these points has infinite multiplicity. The bottom, the lowest eigenvalue, its eigenspace is comprised of holomorphic functions somehow. Okay, and this behavior is called Landau levels. Okay. And today I will be interested in the case where b is really not constant, but it's not very far from being constant. Okay, so you should think that b is varying between 1 and 1.2 or something. So it's really not constant, but it's also, not doing anything crazy at infinity. Okay, as I told you, I don't have a lot of motivation to study these things, so maybe I'm going to give you maybe a better motivation. So if you have a magnetic Laplacian, you can always do a gauge transformation. And this is because in your one form A, you can always, what's important is dA, so you can always add a potential. Okay, so you can do this thing, And obviously, you can also pull back your operator by a diffeomorphism. Okay, so now it's still a magnetic Laplacian. And then you can do a metaplectic transformation, which is just an integral transform with quadratic phase. Okay, and now it's not differential anymore, but it takes a better form. So the form it takes now is that this operator, after all these things, is transformed into this HL, and L is a pseudo-differential operator, and here for convenience we rescaled one variable while we did not rescale the other one. So it's H semi-classical in the x2 variable, and it's not semi-classical at all in the x1 variable. Okay, and after this change of variable, well, the symbol, it really looks like a harmonic oscillator. So you have a function b tilde square, you have a psi1 square, then you have a x1 square if we forget about this alpha thing, and then you have a sub-principal term. And here, the b tilde, the alpha, and the t, they're just functions of these parameters. And here you see this h1 half in front of x1 and psi1 is just because we rescaled everything in x1 and psi1. And so if in the symbol you put just h equals 0, you will find b tilde square of psi2 x2 square times psi1 square plus x1 square, which is just a harmonic oscillator in the x1 and x1 and psi1 variables. And we expect that the magnetic Laplacian, in terms of classical dynamics, we should see happening center guide motion, where you have the particle is turning around very fast, and then the center of this trajectory is just moving around. Okay, so the harmonic oscillator is this very fast rotation movement, and then the center guide motion is related to the fact that the b tilde is not a constant. So the magnetic Laplacian is related to the sub-Riemannian geometry. Okay, and as you see here, it's a model for operators whose symbol vanishes to order 2 on some submanifold, and this submanifold is symplectic. So that's, from I don't know, from maybe a spectral geometry point of view, what's interesting here is that we have an operator, we have a characteristic manifold which is symplectic, and some operator is the solutions to this operator will be microlocalized on this submanifold, and then we expect to see happening some kind of reduced quantum behavior on this symplectic manifold. And so in this case, that's what's going to happen, and that's what's expected, has been expected for a long time, but well, so far we couldn't put our finger on it. Okay. So this operator, it has a very long history. So I think I found references from the 70s where people were interested in the eigenfunctions and the eigenvalues of this operator in this semi-classical setting. I mean, it's just like the electric Laplacian. There's so many things that you can do with this thing that it's really hard to give very comprehensive list of important and relevant work. So the list I put here is very partial. So I must apologize to anyone in the audience who feels slighted by something that I would have forgotten. So an interesting result is from Montgomery in 95. So it's really I'd say orthogonal to the questions that we're interested in, because he's interested in the case where the function b is vanishing somewhere. And in my case, I'm going to assume that b is really not vanishing. So when b vanishes somewhere, Montgomery found out that there's along this, because it's in 2 dimensions, and if you assume some genericity, these lines, it's just lines where b is vanishing. So it showed that along these lines, you have some propagation phenomenon, you have microlocalization on the lines and things like this. Okay. Then there's another direction where, really inspired by the Landau levels behavior, you think of b as a constant, but now you put boundary conditions. And because the bottom eigenvalues, the bottom eigenfunctions of your operator should behave like holomorphic function, you expect that everything is going to I mean, in the good cases, everything is going to take place on the boundary. So obviously, this really depends on the kind of boundary condition that you put, Neumann, Dirichlet, or mixed conditions. And there are many results in this direction, and I think I mean, Nicolas Raymond has many results on this, so I think if you want a good list of results and references, you should maybe ask him. He's like a world expert on the subject, and I'm really not. So I will leave it at that. Then there's also the case of closed surfaces, so there's no boundary conditions, but now there is geometry. And in this case, well, unless the integral of b over your surface is 0, to actually define something, you will need a complex line bundle, and it has relations to geometric quantization, and there's different directions. But an interesting thing that takes place is that you may have different solutions to dA equals b, and like solutions that are really not equivalent, and then that's a mathematical counterpart of the Aharonov-Bohm effect. And then so there's a list of articles on so-called magnetic bottles where basically B is 0, but dA is not 0. I mean, B is 0, but A is not 0, and you have non-compact surfaces, and on the boundary, which are circles, you have some non-trivial circulation of A. And this basically forces the spectrum to be discrete in the good cases. And so you have non-compact manifolds, you have something that looks like a Laplacian, and you have discrete spectrum. So that's an interesting phenomenon. And I think that the reference article on this is the Morin paper in 2001, but just many other papers. Okay, and then I come to the thing that's really interesting me today. It's about magnetic wells. So instead of B vanishing, or instead of B constant, or instead of playing with the A, we're really only interested in the local behavior of B, and we assume that it has a strict non-degenerate minimum, and this minimum is strictly positive. So I think the terminology magnetic wells is from the paper by Elfer and Morin in '96. Okay, and the question already was, how good? I mean, it's not. There's good reason to expect that then you have localization near the minimums of B, but then what kind of optimal localization can you expect? And if you have several minima, what can you say? And I mean, there's basically take all the questions that you have in the case of a potential with non-degenerate minimums, and you can just make the same questions in this context. So there's the best result that I know in the case of just one well is the result by Nicolas Raymond, Saint-Vu and Gogh from 2015, and it's the following. So assume something at infinity. So in here, I assume that B has a limit which is positive at infinity, but maybe, if B goes to infinity at infinity, as long as you're in some functional analytic context where you can make sense of the operator and show it has a self-adjoint extension and legitimate the spectrum and everything, so that the question is well posed. Okay, and also assume that B has a global non-degenerate minimum, B0, also positive. And then what's really important is that at infinity, you're strictly above B0. Okay, that's a really important thing. Then the spectrum of your magnetic Laplacian is discrete below the value that's attained at infinity. Okay, and it's discrete in a strong sense that it's the only points, and each point has finite multiplicity. Now, for the smallest eigenfunctions, we can say a bit more. So we can enumerate them, and each one of them has multiplicity 1. And we have an asymptotics. And here I wrote the first terms of the asymptotic, but we have a complete expansion in powers of h. Okay, and if you look at this formula, you see that it starts with B0h, so the minimum of B. And then you have this h squared. And, if you remove the B0, divide by h, and, take D0 to be 1, D1 to be 1, then that's the harmonic oscillator. So if you see this thing, you will readily think that this is a potential minimum kind of situation, okay? Obviously, the D0 and the D1, they have explicit formula. You can show both of them are strictly positive. Then they can be expressed with the Hessian of B at the minimum. And okay, and the next, yeah, obviously, I mean, all of this, the way you prove such a result is, among other things, is proving that you have microlocalization. So the corresponding eigenfunctions, they're microlocalized near zero. Okay, so there's a result from 2011 before, so this paper from 2015, where by Helfer and Kordyukov, and they obtain, I think, a little o of h squared instead of a full asymptotics in powers of h, and the result is slightly less microlocal in nature. Okay, and so yes, the way, I mean, the proof of this theorem basically is reducing completely the operator. So remember, after a first transformation, our operator was basically a quadratic form in x1 and xi1. Okay, and then in this context, you can do a Birkhoff normal form. First, a classical one, implement it with an FIO, and then you do quantum Birkhoff normal forms. And in the end, up to h infinity remainders and x1 and xi1 infinity remainders, you obtain the function of the harmonic oscillator. Okay, and so that's the way the proof works. And obviously, there's this question that if you want exponential remainders, it's always a problem because the Birkhoff normal form, it only works in C infinity. So you know, it does not converge, so you can't really do it in the analytic category. So because in principle, if you had exponentially small errors in the technical results in Nicolas Raymond and Sandvinger's paper, you would get the exponential tunneling very fast. It would be very much more simple. An important observation here is that this argument is completely local. So I guess microlocal. So if your minimum is attained at several different points, you can just do the strategy from before at each point, and then you will see that the spectrum up to h infinity errors is basically the superposition of the spectrum obtained at each well. So this is only interesting if all the wells have exactly the same form, because basically the asymptotics is determined by the derivatives of b at the minimum. Okay. But anyway, so that, that's what I meant by saying that it's a microlocal result. So you can add the spectrums and you can add the multiplicity up to h infinity errors. So after all these observations, the question now is the question that we were interested in is the case where the function b has some symmetry, and then this symmetry should, be lifted to the operator A, and then the eigenfunctions and the eigenvalues. And so in the presence of symmetry, you expect that you will have pairs of eigenvalues. And because of the existing results, you know that they are very close. And you know that these pairs are separated by some power of h, which is quite precise. It's this, in the formula that in the picture that I drew here. And so the true question is whether these pairs of eigenvalues are equal or not. And as usual, we can only answer this question by actually computing an equivalent for the difference. So we will find an exponentially, an exponential equivalent, but what's really important is that they're not the same. And because they're not the same, it means that, under quantum evolution, the eigenfunction, a solution will just go back and down, back and forth between the wells. Okay, so from now on, I'm really interested in the lambda 1 and the lambda 2. I guess our strategy would also work for lambda 3 and lambda 4. You take a finite number of eigenvalues, it can probably work. But I mean, I hope that maybe in the future you have something a bit more robust, that it's more efficient to look at excited modes, you know. So I mean, I'm going to forget about all the other eigenfunctions and eigenvalues and just concentrate on the first two ones. Okay. And so that's the question that Morin already asked in 96. And they suggested that the difference between the two eigenvalues should be of the order exponential minus constant over square root of h. And it turns out that it's not, it's exponential minus constant over h. So there's this thing that so when people work with a tunneling effect in the electric case, there's this very strange thing that you can take the potential function to be C infinity and still obtain some results. And, you know, with exponentially small errors. And that's because the electric Laplacian is a very special operator. Now, in the case of the magnetic Laplacian, it's not really, I mean, I don't think it's really reasonable to expect that if the B function is only an C infinity, you will get any interesting thing. In particular, with only C infinity assumptions on the function B, you will see that in most cases, the decays you can obtain are of the order exponential minus constant over square root of h. That's I mean, this kind of scaling is really because if you work with C infinity functions B, that's the kind of scaling, this kind of decay that you will obtain. But in the analytic case, it gets really the true exponential decay. But usually to get it, you have to go through micro-local arguments, and what happens with the electric operator is that somehow you can rely on purely local arguments, you know, just conjugate your operator with some exponential weight and, you know, do some commutators and use the specific form of the operators, and then, you know, it just kind of works out, but it's really specific. Okay. So as I said before, the only result of quantum tunneling from already known before, the result I'm going to talk about, is the result by Soren Fournais, Léo Morin, Nicolas Raymond from last year. And they have a very special assumption, is that the function B is basically constant everywhere, except in two disks. And in those disks, the function is radial. So as you can imagine, this is really not a very generic assumption, okay? Even in any kind of generic situation. And so inside of each disk, there's only one minimum, which is attained at the center of the disk. They have to assume that the disks are sufficiently far away. So if you think of the disk as having diameter 1, they need to be separated, you know, a distance at least some constant, and the constant is explicit. I don't remember, maybe it's square root of 2 or something, you know. But in any case, they obtain that the difference of the first two eigenvalues is exponentially small with an equivalent. And on purpose, I didn't write anything more because the constant C, the constant S, and the constant beta, all of them have very complicated expressions. And the way this works is that because the potential is radial, inside the disk we have some formula, explicit formula for the eigenfunctions. And then outside the disk, because the B is constant, we also have explicit formula. And so, you know, it's kind of connecting everything together and writing out everything. And in the end, you have some very big integral and it's complex stationary phase. And it's interesting because it gives us a positive result, you know, and it shows us that something is possible. But the method is really specific to this very special situation of radial symmetry. And the funny thing is that B only needs to be C infinity inside the wells. But somehow, being radial it's an analytic assumption because you're constant in the circles. And if you're constant, you're analytic. So you're only partially C infinity, you're also partially analytic. And I mean, in many situations that, you know, there's no way that this is a important observation, but in this case, I think it's very important. Okay, so now I can show what's our result. And our result does not imply the previous result. It's a, you know, different result. So now I have a function b, which is only analytic in x1. But I think for the benefit of this talk, you may think of b as being analytic in both variables, you know. But in any case, it turns out that being analytic in x1 is, you know, sufficient. That's okay. And it has a double symmetry, which is that if you replace x by minus x or y by minus y, you just get the same value for b. Okay, now I also assume that we have wells which are situated on the vertical axis and symmetric, obviously, because of the symmetry assumptions. They are the only non-degenerate minimum. The value b0 is only attained at such points. At infinity, the b has a limit, which is b1 strictly more than b0. Okay. So that's the assumptions that we need so that you know, the operator is well defined, has a well-defined spectrum. The spectrum is discrete in the region we're interested in. What's the crucial assumption here? So there's a crucial assumption is that the minimum of b, because b is analytic in x1, we can, you know, consider complex values of x1. And we assume that if we go from one well in the on the top to the bottom well and along the complex values of x1, we can follow b0. So b equals b0 has a solution in the complex domain, and this solution is smooth in x in y or x2. So that's really a crucial assumption, so that, you know, between your two wells, you can go from one well to the other along a smooth path. If you take a random function that's analytic in x1 and has the double symmetry, you can certainly find many functions that do not satisfy this assumption. Okay, and if you work with the electric Laplacian, you will see that it's a crucial part of the argument all the time, that you can follow the characteristic manifold you can parameterize it as a function of something else. So, okay, so that's why I'm just insisting that it's a crucial assumption, and if you don't have this, I mean, I really don't know. I expect that something is possible, but it will be a different situation. Then we have also some smallness assumption, which are more or less important. So basically, we're assuming that b is varying between b0 and 1 plus epsilon b0, so that, you know, it's really inside of a strip. And then we're also assuming that the derivative of b with respect to x1 has some kind of sign. These assumptions are more technical, and so I'm not going to go more into details. In any case, then we get the same conclusion. That is, the difference between the first two eigenvalues is asymptotic to some exponentially small number. I have to say, that's a bit the twist in this story, is that usually when you get exponentially small estimates on the difference of eigenvalues, you also get exponentially sharp estimates on the eigenfunctions. And we don't. So somehow we get exponentially sharp estimates on the behavior in the y variable, but we don't get that in the x variable. So in the x variable, we get actually, we rely on quite poor estimates actually. So that's a bit of a surprise, I guess. But because of b being analytic in x1, we're able to reduce everything to x1 equals 0. So that's what's happening here. Yes, last one before I try to explain a bit how we do this. In our case, the constant c, well, we don't have a formula yet for this. So it's some constant. It's positive, but we're still trying to work out the formula for it. But I think you will have some mercy for us, because if you've tried to do it in the electric case, you will have seen that the constant C, even in the simplest 1D electric case, is already not a very nice constant. In higher dimensions, it's worse, and here we're in 2 dimensions. So in the electric case, it would also already be a nasty constant. So yeah, so it's not so bad that we don't know C. The S function is really somehow an action, and it's related to the integral of A along the solution of B equals B0. So it has some symplectic geometry interpretation, I guess. And the constant beta, I don't remember actually, I should have written the constant, but beta is like 5/2 or 3/2. So beta is, there's not a lot of information in the constant beta. Because in the other case, the beta constant, it was like 1/2 plus B0 over B1, where B0 and B1 are some numbers that come out from, the study of the operator. So beta had some content. And in our case, beta does not have such content. So that's for the result. And now I wanted to say a little bit of how we proceed to prove such a thing. So as I said before, we can forget about the magnetic blah blah and just reduce everything to an operator whose symbol is vanishing to order 2 on some submanifold which is symplectic. Okay, so that's really what we're working with here. And then, you can interpret everything in terms of the original B function. So the B tilde here, you can interpret it in terms of the B function, but that's just at the end of everything, when you want to understand what exactly are the formulas that you're writing down. So that's not really crucial for whatever I'm going to say now. And then it was more convenient for us to work with symbols that are operators. So we're going to work, see the operator from before as a pseudo-differential operators in the x2 variable valued in operators in x1. And these operators in x1, it turns out that they're pseudo-differential, but they're not semi-classical. Okay? And so with this point of view, we can see that the principal symbol now it's really a harmonic oscillator. And the strength of this harmonic oscillator is B tilde squared. I mean, it's B tilde. Okay. Okay. And now at the start, I said that B has to be analytic in X1. And so I mean, you will have to believe me that after all these transformations of gauge transform, diffeomorphism, and metaplectic transform, the B function, I mean, this P operator, it depends analytically on the Xi2 variable. Well, if the original B function is analytic in all variables, then P is certainly analytic in Xi2. But what's crucial is that if you just remove analyticity in X2, it's still analytic in Xi2. Okay, that's not a very big claim. Okay, and that's crucial because then we can conjugate the operator with C-infinity weights in space weights. And then we have a nice formula, and obviously this is not true. You cannot do this if the symbol is not analytic in Xi2. Okay, so that's the only, I mean, that's where we really use analyticity. Because once we've conjugated the operator, then we're just going to do C-infinity macrolocal analysis on the operator. And so now the principal symbol after this conjugation, it becomes P0 of x2 Xi2 plus I phi prime of x2, where phi is just your weight, okay? And because this is a harmonic oscillator, even though, because once you've done this function P0, it's a harmonic oscillator with strength B tilde. But B tilde, now it's a function of a complex argument, so it's complex valued. So originally we have a harmonic oscillator with real coefficients, so it's a nice operator. Now it becomes a complex valued harmonic oscillator but because of the real parts being in the right place, we can still, we still have a reasonable spectral theory for this thing. So we know his spectrum. And the spectrum is, what you expect, which is just a half integers times the strength of the field. Okay? And so you see that so that's it's n needs to be at least 1. Yes, it starts at b tilde. It doesn't start at minus b tilde. I'm sorry for this typo. So it starts at b tilde. Okay, and the next one is just 3 times b tilde. But because we're looking only at the bottom of the spectrum, you can see that we're going to be only interested in the first eigenvalue of p0. Okay. Now, you see here, this thing here depends on the weight, capital phi, and we want to understand exactly what happens at the level b0. So we're going to take the phi so that b tilde of all these things equals b0 at the largest space possible. And the choice that gives you this is taking a weight which takes b tilde to be equal to b0. And then psi2 equals 0 will be your new characteristic manifold, and you expect that you have propagation in this direction. And so to be able to define this best weight, it's at this place that we use the crucial assumption that you can link one well with the other one with a smooth path. Because you can make this link, then you have a smooth weight that that's working almost all the way from one well to the other one. And obviously, as usual, also in the electric case, when you get to the other well, you can still define the weight phi, but you will have the problems defining everything else. But at least the weight works until the other well. It's also a usual thing that we're not quite able to work with the best weight. And so instead of working with the best weight, we take another one which is, slightly smaller. And then we're going to, approximate the best weight by taking a sequence of things or making the weight phi being depending on h or, all sorts of technical things. But basically, we need to think of capital phi being something that's, almost equal to phi, but not quite. Okay. And then there's the classical way of proving a tunneling effect. So I think for people who have already proven the tunneling effect in their lives, that could probably be very classical, but if you haven't, there's a bit of a technical thing to do, so I'm just trying to explain it. So now we have 2 wells, and at each well you're expecting that you will have, your eigenfunction will be localized at these wells. And now you want to compute the difference between the eigenvalues. And if you try directly to build quasimodes and find something out of this, it doesn't really work out. So there's a way to, make it work. So it works in this way. So the first thing to do is to actually have eigenfunctions, true eigenfunctions, that are localized in only one well. And you cannot do this with the original operator because you assume that the eigenfunctions are localized in both wells. So here you just put something in one of the wells, and it's this function sigma. It's a bump function that's just going to kill one of the wells. Okay, and now you have an operator which has only one well, so you can apply the usual theory, and now like in a C-infinity microanalysis framework, you have one eigenfunction with eigenvalue more or less equal to the true eigenvalues of the true operator, and you know that the multiplicity is 1, and you know that it's localized in the right place and everything. So for all these things to work out, you need to assume that your weight, capital phi, was less than the best weight. And the way this turns out in the computations is that as long as the capital phi is not too large, this conjugated and modified operator is still elliptic. So it's basically an ellipticity estimate that's going to tell you that you have discrete spectrum in the right place. And then because you have a family of operators that all of them are elliptic, they're all deformations one of the other, and then you prove that actually the spectrum does not depend on the weight phi, and that the eigenfunctions, they don't really depend on the weight phi because they are given by this formula, like because it's just a conjugation of operators. So that's the first step. So the first step is, it's actually two sub-steps. The first one is to build new eigenfunctions. And then the second step is to prove that these new eigenfunctions, they actually are localized in the right way at the right place with the right eigenfunctions, the right eigenvalues. Okay. Now, the third step is to build BKW expansions for the eigenfunctions. And so here it's a slight twist from the usual thing, I guess. I mean, at least for me, it was a twist. So because we're working with operators that are operator valued, I mean symbols that are operator valued, we kind of separate the things. So basically, you have your harmonic oscillator, which is the eigenfunction is the bottom one is the Gaussian, and then you can write the construction in this way. So what's really crucial here is that the U plus, so supposedly the model for the eigenfunction, it has an exponential weight that only depends on x2. And then, what's between the brackets is a C infinity BKW expansion. So in particular, in the variable x1, the localization is not better than localization in C infinity category. Okay. And certainly, if B is analytic in x1 and x2, we expect that U plus is exponentially well localized near x1 equals 0. But actually, we don't care. That's the beauty of what's happening here. Okay. And now there's the construction to make all those things work together. So you observe that you have, so I created these new eigenfunctions, U0 plus, but the problem is that it's an eigenfunction for the wrong operator. So I kill the thing that I added to bridge the gap. I added some sigma function, and now I multiply my U0 plus by some chi function, so that this V plus, it's supported in the region where the original operator and the deformed operator are the same. Okay. And because of this, it's almost obvious that this thing is an exponentially good quasi-mode for the original operator. And I mean, if you try to plug in the BKW formula, you will not get this. You really need to create this auxiliary eigenfunction to get this. It's a kind of a trick, And then you need to remember that you had two wells, so you could do the bottom and the top thing. So now you create a V minus, a U0 minus, and all those things. And then there's like a nice formula about matrices, 2x2 matrices, that tells you that the difference of eigenfunction, of eigenvalues, is given by some scalar product. And then you just, now you approximate the U0 plus by the BKW expansion. Nice integral, you compute everything, and that's the end of the proof. Okay, so this last step, I mean, there's nothing really exotic taking place here. And what's really important is the step 2 and the step 3, okay? Because the step 1, as I told you, the step 1 is just a normal form. The step 4 is the usual argument, okay? And so what are we doing in step 2 and 3? So basically, we're doing this operator valued symbol Grushin reduction. So as I said, the principal symbol is a harmonic oscillator, so the resolvent has a very nice behavior. Okay, and so you can set a Grushin problem. So you take the original operator, which I decided to call P minus Z here. I think it's a L minus Z, but no matter. And then you take the eigenfunctions and the kernel and the co-kernel of P0, you add them in your matrix, and you prove that this thing is invertible. So you have now an operator which is it's a system of operators, and the principal symbol is invertible. Okay. Now you can build the parametrics. The usual, it's usual C-infinity macrolocal analysis just for systems. And now you have this Q thing, and the QW and the WQ are almost one. And here, the QW equals 1. That's going to give you ellipticity, because basically you rewrite, you need to write out what's the Q, what's the W, and that's going to give you ellipticity. Now the WQ, it's going to give you the BKW expansion. Okay, and as all, it's always like this. Once you find the solution of a complicated problem, it seems to be a bit trivial. So once you've written everything in this way, the computation follows from the usual, relatively usual things, with the caveat that it's obviously a bit technical. So why is it technical? The first thing is that we added this sigma function, and the sigma function is local. So you're starting from the top well, and you have the bottom well. So this sigma function, it needs to be localized in a very small neighborhood of this well. So you have to control, that some constant don't blow up when you do this thing. And then the weight, capital Phi, as I said, it needed to be smaller than the best weight. But you will not be surprised to find out that it needs to be sharply, almost equal to Phi. And for this, it needs to depend on small phi and also of H. And if you do this correctly, it turns out that you have something that loses half powers of H when you differentiate. And, well, I think you all know that can be a problem. So, yeah, okay. So there's a long list of technical things that take place, but it's more really technical problems. Anyway, so I think that's all. That's everything I wanted to say so far.
Thank you very much for the talk. We have time for questions, so you can unmute yourself if you have questions, or just write them in the chat and we will relay them.
So would you have a natural assumption a bit like that for 3 wells, like in terms of the symmetry and things like that? Could you come up with a setting which would make sense? Or 4 wells, if you prefer.
Okay, so the first observation is that we assume that we have symmetry with respect to X and Y. In theory, it would be sufficient to assume that B of XY equals B of minus X minus Y. However, I think the proof does not work. Because we're really using, or at least not without a lot of modifications. Because we're really using the fact that it's completely localized on x1 equals 0, and the fact that we're doing C-infinity analysis on x1 is because there are many things, because the symmetry, everything that can go well goes well. So already to remove one of the symmetries, I think it's possible, but it's not contained in the result so far. So I really hope that we can improve the argument, you know, and get a better assumption. But you know, that's the kind of level of difficulty that we are in. In principle, if you have 3 points and you have a rotation invariance by 2 pi over 3 or something like this, I would expect that there's also a result. I just don't know about the proof, you know.
Okay, and what's the kind? So you said it was a bit of an action, the S that appears in the well, the quantities that appear in your expansion. You have a bit more information about how they depend on the geometry. I guess they depend on the values of your function.
So if I remember correctly, you have B equals B0, which is a line in the complex domain. And now you integrate the A. So we need, at some point, we choose a good gauge condition. Basically that the A is only concentrated in the AY. So A is just A dy. And then you integrate this A along this curve in the complex domain. So it's a circulation. And if you want to see it as a closed curve, well, you have your bottom well and you have the top well, and you're going from, you know, you're going up and then you're going down and you take half the sum. Yeah. So now it's a closed curve, but it basically that somehow the characteristic manifold, it's a complex surface that has 2 particular points on it. And they are joined by these particular points, they're points of self-intersection of your curve. So now you have one curve. You can join those 2 curves in 2 different ways. I mean, I couldn't give you a better interpretation of this, but the problem for me is that even in the electric case, I'm not really sure I can give you a better explanation. I mean, in the electric case, it's very simple, you know, integral of square root of v from one well to the other. So if you're satisfied with this, then, you know, okay. But in terms of symplectic geometry, it's not quite clear for me why, you know, I mean, the computation gives you this, but to interpret it better, I don't know. It's kind of it's kind of a problem, actually.
Anyone else wants to ask a question or comment on the talk? If not, let's thank Yannick again. Merci beaucoup. And I believe this was the last talk for the year. And we will be back in January, on January 13, actually, with a talk by Rupert Frank. Until then, happy holiday to everyone.